Welcome to Regents Review, Unit 6 on bonding. When we have a chemical bond and we want to break that bond, that attraction between these two atoms, we have to put energy in. So energy is absorbed to break that bond. When a bond is formed, the opposite happens. Energy is going to be released. And in a lot of chemical reactions, we have both things occurring. So if you look in this reaction here, H2 plus Cl2 yields 2HCl. We have to break the HH bond and the Cl-Cl bond. So we're putting energy in to break those apart. And then when we form the two new bonds between the HCl and the other HCl, energy then is going to be released. So overall, there's a net either gain or loss of energy depending on the reaction. And that net gain or loss is what we call delta H, and that's located on table I. Okay, recall that atoms will bond, or form a chemical bond, to obtain a lower energy state. And this is done by obtaining a full valence shell. And if you look at group 18, our noble gases, these are our inert stable atoms. They have a full valence shell, which is typically 8 valence electrons. We call that a stable octet. With the exception of hydrogen, hydrogen can only have a maximum of 2 valence electrons when it has a full valence shell, and we call that a stable duet. The three classifications of bonds that we have are, the first one is the ionic, occurring between ions, and that occurs between a metal and a nonmetal. The metal has a low electronegativity, so it has a low attraction for electrons. The nonmetal has a high attraction, and so the nonmetal takes the metal's valence electrons to get a full valence shell. So there's a transfer of electrons from the metal to the nonmetal. And the resulting properties, ionic compounds are typically hard. They're good conductors in the aqueous, so in solution, or in its liquid molten state. And that's because it has free moving ions when it is dissolved in water or when it is in the liquid form. As a result of the ionic bond, we have a high melting and high boiling point for ionic substances. Covalent compounds, co means share, valent means valence, so they're sharing valence electrons. This occurs between nonmetals. Because nonmetals have similar electronegativities, they have a similar attraction for electrons, no one wins this kind of game of tug of war, and so they end up sharing these electrons, either equally or unequally. And the resulting properties, they're typically soft, they're poor conductors of heat and electricity because they don't have these charged particles like the ionics do. And they have a low melting and low boiling point. And then we have the metallic bond. The metallic bond is very similar to the covalent bond. It just occurs within metals. And the interesting about metallic bond is that they have a sea of mobile electrons. So they end up having these delocalized electrons that kind of move around in between the atoms. And because of that, metallic substances, so our metals, can conduct in the solid state. So they're the only substance that's going to conduct in that solid state, whereas the ionic conducts in aqueous or liquid, and covalent does not conduct. Metallic substances have a high melting point. They're said to be malleable, which means we can bend them, or we can kind of flatten them into sheets. And they are ductile, which means we can pull them or draw them into wires. As we talked about those ionic compounds and why they can conduct in the aqueous form, it's because when we take a ionic substance, the solid here, overall it is neutral. We place this into water, it's going to dissociate into individual ions. And these ions, these moving ions or charges, allow for the conduction of electricity. So ionic substances are said to be called electrolytes because they conduct electricity. In our Lewis dot diagrams, looking at the ionic diagrams, recall that metals form positive ions and they have no dots and brackets, as we have here. And nonmetals form negative ions and they always have 8 dots in their brackets. Because the metals are losing their valence electron, we call that ionic compounds as a transfer of electrons from the metal to the nonmetal. So the metal is losing this valence electron and it's being transferred over to the nonmetal. So they both get a full valence shell. So when we lose this one negative charge, it becomes positively charged, as indicated here. And when this chlorine gains this extra electron, this extra negative charge, it becomes negatively charged by that one electron. So there's more negative charges compared to positive charges. And then these two separate charges will attract each other and form an ionic bond. So we show the metal dot diagrams as just the symbol, the brackets, and the charge, no dots indicating that transfer of electrons, and for the non-metals, always 8 dots, brackets, and the charge. Here's an example here for calcium chloride. So we have one Ca, we have two Cls. So I put my Ca here, and I have my two Cls on the outside. Notice the overall charge is still 0, because compounds have an overall charge of 0. Okay, let's look at how we draw our Lewis dot diagrams for covalent compounds. Okay, let's look at how we draw our Lewis dot diagrams for covalent compounds. So the first thing I want to do is I'm going to write one of my substances here. Hydrogen has one valence electron, and then the other hydrogen comes in and brings its valence electron to share, and so now we have a full valence shell for hydrogen, because recall that it's going to be only 2 valence electrons. For chlorine, I'm going to draw one of my chlorine atoms. It has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So I just distribute those clockwise. And I have one unpaired electron. That's going to be where I'm going to bond. So I bring in my other chlorine. First complete the bond. 1, 2, 3, 4. Now I can skip over that bonding site. 5, 6, 7. And now both chlorines have a full valence shell of 8 electrons by sharing that pair of electrons in the center. For CH4, so what I like to do is I draw the most electronegative element in the center, or we say the unique one, the one that's only appearing once. So I'm going to draw my carbon in the center. It has 4 valence electrons. I have 4 bonding sites, and this way I can bring in hydrogen, and that brings 1 valence electron with it. Same thing for the next one. And so the carbon has its full valence shell, and each hydrogen has its full valence shell of 2. H2O, I'll start with my oxygen. It has 6 valence electrons. 1, 2, 3, 4, 5, 6. So I have 2 unpaired electrons, so I have my 2 spots to bond. So I bring in my hydrogens. Again, they bring 1 valence electron. And so now we have our bent-shaped molecule of water. For ammonia, we'll start with our N. It has 5 valence electrons. 1, 2, 3, 4, 5. I have 3 bonding sites, my 3 unpaired electrons. So I can bring in my 3 hydrogens. Each one brings in 1 valence electron to share. And now everyone has a full valence shell. Let's look at carbon dioxide. So I start with my C. My carbon has 4 valence electrons. 1, 2, 3, 4. I'm going to place my oxygens on each side. I like to keep it very linear if I can. So I'll put 1 oxygen on the right and 1 on the left. Each oxygen has 6 valence electrons. So first complete the bond. So 1, 2, 3, 4, 5, 6. And do the same thing for the other one. Complete the bond. 1, 2, 3, 4, 5, 6. I now have unpaired electrons. And these unpaired electrons can only pair up in the bonding site. So they're going to slide into the bonding site and share between the carbon and oxygen. So I'll redraw this. So carbon is going to have a double bond because now we're sharing 2 pairs of electrons between the oxygen. And then the oxygen electrons, you can leave where they are, or you can just distribute them evenly like that. So we have that double bond. For the O2 molecule, we'll start with the O first. 6 valence electrons. I have 2 places to bond. I'm going to keep this linear, so go across. First complete the bond. 1, 2, 3, 4, 5, 6. So notice again I have 2 unpaired electrons. They're going to pair up in the bonding site and create a double bond. So I'll redraw that here. And so now everyone has a full valence shell. And last but not least, the nitrogen. I'll start with the 1N first. That has 5 valence electrons. 1, 2, 3, 4, 5. I now have 3 places to bond. Again, I like to keep things linear, so I'll put 1 here, let's say on the left. complete the bond first. 1, 2, 3, 4, 5. So now we have 2 unpaired electrons on each end. So they're going to pair up with the other 2 in the bonding site, and they create what is called a triple bond, which I'll redraw here. So when we have a pair of electrons, which is 2 electrons, we have a single bond represented by 2 dots, or you can use a line. Double bond would be 2 pair or 4 total electrons represented by 2 lines. And triple bond, as in that nitrogen example, we have 6 electrons or 3 pair represented by 3 lines. For covalent bonds, as we mentioned, they're sharing electrons. They can either share equally or unequally. So the non-polar, not polarized covalent bond, we have equal sharing of electrons, as you can see here, between the 2 nuclei. And so the electronegativity difference from table S between these 2 things is going to be between 0 and 0.4, so essentially almost equal. So obviously any diatomic is going to have a difference of 0 because they both have the same electronegativity, and the difference between carbon and hydrogen is going to be exactly 0.4, so it's still essentially equal sharing. So these are nonpolar covalent bonds. They're sharing the electrons equally. A polar covalent bond, so here would be our nonpolar. A polar covalent bond is one atom has a greater pull on electrons. Not strong enough like an ionic where it actually transfers electrons to it, but strong enough that it's unequal sharing, as you can see here. And so that's when the electronegativity difference is greater than 0.4. An example between oxygen and hydrogen, or hydrogen and fluorine. So when we compare all them, nonpolar covalent bond sharing equally, polar covalent bond sharing unequally, where one side becomes partially negative and one side becomes partially positive. And then when one atom is so strong that it can actually take the electrons or transfer electrons, we get a situation called ionic, where we actually form separate ions. So how do we determine the type of bond? Well, the first thing you do is figure out who's involved. If it's a metal and a nonmetal, we say it's ionic, and that's it. If it's a nonmetal and nonmetal, it's covalent, and then figure out, is it nonpolar or polar? So look up the electronegativity difference between the 2 atoms. If it's less than, if it's 0 to 0.4, it's going to be nonpolar, and if it's greater than 0.4, it is going to be a polar covalent bond. So we just talked about bond polarity, the polarity of the bond between atoms, as in the case here. Now we're going to look at the molecular polarity, and this is the polarity of the entire molecule, and that focuses on symmetry. Nonpolar molecules have a symmetrical distribution of charge, as in the examples here, and polar molecules have an asymmetrical distribution of charge, as we can see here. The acronym we use was SNAP, so it's symmetrical nonpolar, asymmetrical polar. So we look at a nonpolar molecule. They exhibit symmetry. Here we have the same atom on both sides, and same thing here. And what I'm showing you is the partial charge. So if you imagine the oxygens are kind of pulling the electrons towards them, and since we have electrons being pulled in this direction and this direction, we have a symmetrical distribution of that charge amongst this molecule, and that's why it's nonpolar. In the polar molecules, we don't have that because the molecules are not symmetrical. Since this molecule is not symmetrical, electrons are going to be pulled closer to the oxygen, and so we create a partial negative side and a partial positive side. And so it's a non-symmetrical distribution of that charge. And the same thing in water, as the electrons are being pulled towards the oxygen side, and the same thing for ammonia, they're being pulled towards the nitrogen. So on a Regents problem, just make sure that you're focusing on what the question's asking. If it asks for bond polarity, keyword is bond, that is the electronegativity difference. If they're asking for molecular polarity, you're looking for if it's symmetrical or not. And that sets up this molecular geometry, these shapes. So when it's straight across, it's a linear shape. When we start to add more atoms or more valence electrons on that central atom, we get this bent shape, such as water. Then we have the pyramid or pyramidal. And we have 4 atoms around the central atom. That's the tetrahedral. Recall that like dissolves like. So if you have a polar molecule, it's going to dissolve in another polar substance, like water, for example. So things that dissolve in water are polar. And if it's a nonpolar molecule, then it's going to dissolve in a nonpolar substance. So again, like dissolves like, and that's why oil doesn't dissolve in water, because oil is nonpolar and water is very polar. And last but not least, we have our intermolecular forces of attraction. This is the attraction between our molecules. And so there are varying degrees of attraction, but the strongest intermolecular force of attraction we have occurs between hydrogen and either fluorine, oxygen, or nitrogen. So H bonding is fun. So hydrogen bonding sets up that attraction between this hydrogen here, for example, in water, and the oxygen here. And this is the reason why water has a fairly high melting and boiling point for a covalent substance. So other substances that have hydrogen bonding are things, again, like water, NH3, our ammonia, and HF. And so the stronger that intermolecular force, the higher that melting and boiling point.